Hello, everyone. Welcome at our Solfair colloquium and webinar of solar physics of global reach. And today we have a talk by Jim Klimchuk about heating of the magnetically closed corona. So Jim is well-known expert in the field. Let me very briefly introduce him. So Jim has been in the heliophysics science division at NASA Goddard for the past 13 years. Before that, he was at Stanford and then at NRL. He received his PhD from the University of Colorado. Jim was always very active in community service, having been elected president of AGU's Space Physics and Aeronomy section and chair of the Solar Physics divisions of the AAS. He is currently a member of NASA's Heliophysics Advisory Committee. So, Jim, please go ahead and you have your 45 minutes. I will warn you 5 minutes before the answer, please.
All right, very good. Well, thanks, Gregory. Good afternoon to everybody. When Gregory asked me to give this talk, I figured I would discuss pretty much exclusively those aspects of coronal heating that bear on the discussions we've been having within the sulfur team. But Gregory thought, no, it'd be much better to have a general talk. So that's what I've tried to prepare. Of course, coronal heating is a huge topic. You can't cover it in an hour. So I'll be limiting myself, first of all, to the heating of the magnetically closed corona. So places where the field lines are rooted to the surface at both ends. That means active regions, quiet sun. And also, sorry?
Some echo.
Is there echo? Something I should be doing? Still echoing?
No, please go ahead. Okay. I will mute, and I ask everyone to mute your microphones to avoid these echoes.
All right, thanks. So then the second way I'll limit the discussion is by only considering heating that's related to magnetic reconnection. You know, wave heating, of course, is playing a role. It's in fact playing a very dominant role in open regions and the solar wind. But most people feel that wave heating in the closed regions is weaker than reconnection-based heating. Maybe Inigo will jump in there and correct me on that, but it's not a closed issue for sure. There's a debate going on, but I think by and large, people think reconnection heating is stronger in closed regions. Okay, well, to many folks, the coronal heating problem is all about understanding the detailed mechanism by which magnetic energy is converted into thermal. But I take a broader view. I mean, to me, the coronal heating problem is to explain the non-uniform thermal structure. Move this, sorry. Is to explain the non-uniform thermal structure and emission properties of the corona, including the solar spectral irradiance. And I remind you that this irradiance is an important driver of space weather. The X-ray and UV emission from the sun, the variable emission, is a very important input to the terrestrial upper atmosphere. It controls the conditions in the terrestrial upper atmosphere, and therefore it affects things like satellite drag and the propagation of radio signals. So obviously many systems are impacted. And this is true not only of the short timescale variability of flares, but also the longer timescale variability associated with the evolution of active regions. So to solve this problem, we need to understand three things. First of all, how is magnetic energy built up in the coronal field? Second, how, when, and where is it released? And third, how does the plasma respond and radiate? Now, these all involve an enormous range of spatial scales. Furthermore, there are important physical couplings between the scales and between different parts of the atmosphere. And it's for this reason that the coronal heating problem is so very challenging. It would be fantastic if we could perform one massive do-it-all numerical simulation that treats everything, but it's just not possible. It's not feasible, not even close. So consequently, we're forced to look at different aspects of the problem individually. However, it's very important that we keep track of the progress that's made by others that are studying other aspects of the problem, because ultimately everything has to fit together in a comprehensive, unified, coherent picture. All right, so let's first take a look at the first sub-question. How is energy built up? Well, that's really an easy one. Here is a first light movie from DKIST. This shows the photosphere over about 10 minutes. And as you're well aware, the photosphere is undergoing turbulent convection. And so these chaotic flows then are driving the coronal magnetic field up above. The bright patches you see here and there in the intergranular lanes, these are places of intense magnetic field where the strength is kilogauss. And emanating from these patches are coronal flux tubes, topologically distinct flux tubes, and I'll oftentimes refer to them as strands because they're so thin. Well, these strands reach up into the corona, they flare out to become space filling in the corona because the corona is low beta. And the places where they meet, their boundaries, these are current sheets. So we estimate about 100,000 of these strands in a single active region. So there is an enormous number of current sheets up in the corona. All right, well, these convective motions are causing the coronal field to become tangled and twisted, and stresses are building up. And eventually some sort of critical conditions are met, and the field suddenly breaks. It releases energy very suddenly in an explosive reconnection event. And that's what we call a nanoflare. Now, our friends at PBS can explain this much more dramatically than I. I'm going to show you a fun video clip here. You might want to turn up your volume. I did a test with Gregory the other day, and he said it was a bit faint. But this is a clip from a 1-hour TV special that was put together before the eclipse of 2017. And they consulted me on coronal heating. And based on what I told them, they came up with this. Hope you enjoy it.
The arches of plasma that rise from the sun's surface can be made up of many magnetic field lines. As the sun's plasma churns at the surface, it can twist and tangle these magnetic field lines, creating stresses that build up until eventually the lines break and reconnect in a simpler configuration. This releases huge amounts of energy in a nanoflare. Millions of nanoflares are thought to be going off each second, beginning at the sun's surface and reaching into the corona to heat it to over 1 million degrees.
Okay, so if that didn't motivate you to study nanoflares and coronal heating, I don't know what would. Well, so what is it about the conditions that lead to nanoflares? What are the critical onset conditions for fast reconnection? This is a very important question because it determines how energetic the nanoflares will be. If the onset conditions are mild, then we don't build up much stress in the field, and the nanoflares are relatively weak. If, on the other hand, the onset conditions are quite severe, we have to build up a lot of stress before the reconnection sets in, and so the nanoflares will be large and very energetic. And that's true, of course, for all phenomena that involve the explosive release of magnetic energy. It's true for coronal jets, CMEs, flares, magnetospheric substorms. So this question of reconnection onset is really, in my view, one of the most important questions that we have in heliophysics. So I've been trying to study it for a bit now with my colleagues James Leake and Lars Dahldorf. We've been computing MHD simulations of current sheets, and we're looking at individual current sheets because this onset business, it's very sensitive. So it's really important that the current sheet be well resolved. Otherwise, you can't be sure that the effects you're seeing are not some unphysical effects. So really, it's very important to resolve the current sheet, at least for current sheets that are being driven very slowly, as is the case for nanoflares. These convective motions in the photosphere, they're driving the field, but so slowly that the field is in fact evolving quasi-statically. Now that may not be the case for eruptive flares. There the driving is very strong. So whether or not you need a really good resolution of the current sheets in that case is something we need to think about. And I'll refer back to that at the end of the talk. But for these simulations of nanoflare current sheets, we do resolve the current sheet very well. We use a code called Layer3D. It's an MHD code. And MHD is appropriate because kinetic scales do not develop until long after the reconnection has begun. So for the onset issue, MHD is perfectly fine for the solar case. The properties of our simulations are shown here on the left. The important things you need to note are, first of all, that we begin with an equilibrium current sheet. We use triply periodic boundary conditions. And finally, we include a guide field. And that guide field is so very important because the geometry of nanoflare reconnection is one in which the guide field dominates. It's bigger than, and generally much bigger than, the reconnecting field component. So shown here at the top, this is a snapshot of the current density in one of our simulations after it's gotten underway. And these angling features here, these are flux ropes formed by the tearing instability. The reconnection begins with the tearing instability, and these angled flux ropes are the flux ropes corresponding to oblique modes of tearing. We find that the interaction of those modes is very important. It can lead to turbulence. All right, so this view is looking down on the sheet from like a 45-degree angle or so. Next, I'm going to be showing you a view right along the sheet. It's like here on the bottom. I'm going to be showing you movies of the component of velocity parallel to the sheet. So left, right here. Here is the sheet in the middle. Hope you can see my cursor. These streaks here of red and blue, these are outflow jets emanating from the X points associated with the tearing. All right, here we go. Let me just get this started, then pause. Okay, there we are. In fact, here are 6 different simulations. There are 3 simulations on the left that are long current sheets, 3 on the right that are short current sheets. Here's the current sheet in the middle. And long and short is relative to the wavelength of the fastest growing tearing mode. You know, I wish I could take the time to describe why that's important. It's really kind of a neat story, I think. I just don't have time. We'll have to leave that for another seminar. Okay, well, in addition to the long sheets and the short sheets, we have 3 different levels of shear. On the top, we have large shear, medium in the middle, and small shear on the bottom. And these angles here are the amount of rotation of the field across the sheet. So again, this is a movie of the component of velocity parallel to the sheet, the left-right velocity. The color table here will be evolving. It's the same for all 3 long sheet simulations. And it's the same but different for all 3 short sheet simulations. All right.
Jim, could you comment, what are the units of this color bars, color scale?
Oh, what is it? Oh, I don't remember, but what we find is that once the flows get going, we have reconnection, the outflows are pretty much at the Alfvén speed. So the flows are, of order 1,000 kilometers per second.
Okay.
We try to use realistic solar conditions, magnetic fields, densities. So the beta is small, the Alfvén speed is large.
Okay.
So yeah. So, but the flows, once they get going, are Alfvénic. Okay, here we go. Now, there's a lot happening here. I don't expect you to absorb all of it. I can tell you that we find evidence for quasi-orderly formation and coalescence of plasmoids. We find evidence for really messy turbulence. But the important thing to note from this is that all 6 simulations behave differently. So clearly, the onset and early development of reconnection depends upon the length of the current sheet and the shear of the current sheet. That's the main message here. So for the purposes of this talk, the most important thing is the amount of heating. How much magnetic energy is converted into thermal energy and how quickly. And that's shown here. These are plots of the change, of the internal energy. It's ramping up as a function of time. And this energy has been normalized by the free magnetic energy in the original field. Okay, at the top here, we have the 3 long sheet simulations. And this long sheet regime is the regime of eruptive flares. So these simulations are relevant to eruptive flares. What we find is that for all 3 cases, there's a sizable release of magnetic energy. But the rate of energy release is different in these 3 cases. Okay. We find that the level of turbulence, there's some turbulence in all of these simulations. The amount of turbulence is greater for the large shear case, and that presumably explains why there is a faster energy release. Now on the bottom, I show the energy change for the short sheets. This is the realm of nanoflares. Nanoflares are in the short sheet regime here. And the situation is really quite different because only one of the cases, the large shear case, shows substantial energy release. The small and medium shear cases don't do very much at all. There's hardly energy release. So clearly, in the short sheet regime of nanoflares, there is some critical shear angle that must be reached before we get appreciable energy release. Okay, well, we've thought about these simulations quite a lot. We've come up with what I think is kind of a neat conceptual framework for understanding why we get these different behaviors. This framework is based on the relative growth rates of the tearing modes. As I've said, the reconnection begins with the tearing instability. And what's really fascinating to me is that the early development, linear development of the tearing instability, when things are very, very small, they determine what eventually happens in the large amplitude nonlinear regime. So basically, this early evolution sets the stage for what happens later. So we believe that we can predict whether and how, by how I mean dominated by plasmoids or dominated by turbulence, whether and how fast reconnection will occur based on the properties of the current sheet, its length, its width, and its shear angle. Now, these simulations are admittedly quite idealized, so we want to improve their realism. We're doing that in stages. We're adding line tying. We're adding time-dependent thinning and shearing. And we're considering current sheets of truly finite length. As I said, these simulations have triply periodic boundary conditions. So there are limits on the size scales allowed by the system, and in particular, limits on the wavelengths of the tearing modes that are so important. We want to consider sheets that have a truly finite length, so sheets with Y points at the ends. We want to see how that affects the behavior. We don't expect it to affect the onset, but the subsequent evolution of the reconnection could certainly be affected. Okay, even with these improvements, these simulations have limitations. First of all, they don't account for the coupling between the reconnection and the surrounding field. When reconnection happens, there's a change in the magnetic conductivity. That changes the magnetic stresses in the surrounding field, and that then feeds back on the reconnection. That's missing from these simulations. We don't think it affects the onset, but it will affect, in principle, the subsequent evolution. Also, these simulations don't leave open the possibility that one reconnection event can trigger other events nearby. Because the reconnection changes the topology and the stresses, that may mean that nearby current sheets, which are subcritical, are suddenly brought to critical conditions, and they then can reconnect. Finally, these simulations do not account for the coupling with the chromosphere. Now, that probably won't affect the dynamics of the reconnection. However, it will affect dramatically what kind of observational predictions we would make from these simulations. And crucially, these simulations do not include evaporation. I'll stress more during this talk, and you've heard me stress it before. You're probably sick of it, actually. But evaporation can be very important for understanding observations, especially in the coronal heating problem. For eruptive flares, as we've discussed, it's possible if we look early enough in the event, we don't have to worry about evaporation. But in the case of nanoflares, where we're always observing many nanoflares overlapping, certainly evaporation will be there and will be important. Okay, well, to overcome these limitations and consider these other effects that I've brought up, we've run a different set of MHD simulations. This is work done with Kalman Knižnik, Vadim Uritsky, and Rick DeVore. And basically, these are follow-up simulations to some work that Kalman did for his thesis with Spiro. So these simulations are done with the ARMS code. We begin with an initially uniform and straight field in a box, vertical field, if you will. Then at the top and bottom boundaries, which correspond to the photosphere, we impose vortical flows. We have 200 little vortex cells, as indicated here on the left. This is at one of the photospheric boundaries. So we turn on these flows, we twist up the flux tubes, and then they start interacting and reconnecting. Eventually, we settle into a statistical steady state in which the pumping of energy into the field by the flows at the boundary is compensated by the dissipation of that energy in the reconnection events. So here on the right, I show current density at the midplane. This would correspond to up in the corona. It's between the two photospheric boundaries. And you can see that there is a crazy nest of current sheets here, very complex. All right, well, we'd like to understand how these effects would translate into observational signatures. To do that, we have to include thermal conduction and radiation, obviously, and also we have to allow for evaporation. Now, none of those things are in the ARMS code, at least not at present. But we've developed a very simplistic method for accounting for these effects that we apply to the MHD data post facto. So we very crudely account for cooling and for evaporation. And that allows us to generate these maps of emissivity. Let me get this started. All right. So this emissivity, this is at the midplane. So this is up in the corona. This is the emission per unit volume per unit time. So this is not what we would see in a coronal image. A coronal image represents integrations through all this stuff. So for example, suppose we have a line of sight here. The intensity that we would see at a pixel corresponding to this line of sight would be the integrated emission from all this stuff here within the plane. And then different pixels correspond to different cuts here. But nonetheless, this reveals a lot about what the observations will show, and I'll indicate that. So what do we have here? Well, there's this sort of a twinkling going on everywhere as nanoflares are popping off. But in addition, we see areas where there seems to be some sort of collective behavior, a clustering of nanoflares, where many nanoflares occur together in relatively close proximity. This, we believe, is very important for understanding coronal loops. All right. So here at the top right, this is a real coronal image. This is from the HI-C rocket. It's the highest resolution coronal image ever made, in fact. And we see the very beautiful loops that we're all familiar with. Now, people get the idea, the wrong idea, that most of the emission is contained in these loops. In fact, that is not the case. These images, like most coronal images, tend to be misleading in that black in the images is not zero emission, but it's the minimum over the field of view. And that minimum is in fact quite large. So in fact, most of the emission in the corona of an active region comes from what I like to call a diffuse component, a smoothly varying component. Then these loops here are just modest enhancements over the background, 10 to 20% enhancements. So we believe that the diffuse component, where most of the emission is, corresponds to that twinkling that I was mentioning happening all over the place. And in those places where we have this collective behavior, this storm of nanoflares, if you will, those are places where we produce these distinct loops. And it's interesting that the cross-sectional properties of loops, the pattern of emission within the cross-section that we're inferring from observations, is much like the simulation. I've done some recent work with Craig DeForest where we looked at the correlation between intensity and width along individual loops observed by HI-C. And from that study, we've inferred that the cross sections of the loops have an emission pattern that looks something like this. Not in detail, but this is a general concept here. The emission does not need to be uniform. It can be very patchy and very irregular. But these bright patches must be distributed over an area that does not have a large aspect ratio, so somewhat circular. And that means that loops really are tubes, which is what people have sort of thought for no good reason for a long time. They are not ribbon-like. Now, some loops rather, may be ribbon-like, and there are observational indications that that may be the case, but at least the loops that we looked at seem to be more like tubes. So this pattern here matches very nicely the pattern in the simulations, and we then are concluding that, in fact, these loops are due to storms of nanoflares. Well, these simulations also have their limitations. For one thing, the current sheets are under-resolved. So it's possible that reconnection onset may not be treated properly. We need to compare the results of these simulations, these multi-strand simulations, with our single current sheet simulations to make sure there's consistency. Also, we've attempted to account for conduction and radiation and evaporation so that we can predict the emission, but that's done only very, very crudely. So the observational predictions are not accurate. To make accurate predictions, typically we appeal to field-aligned hydro models. So in these models, we assume a rigid magnetic field, a rigid tube, and we see how the plasma evolves within that tube in response to heating. And these models can compute that response very, very accurately and compute a very meaningful, very realistic radiation signature. But of course, the heating must be assumed. The field is not evolving, so we're not extracting energy from the field by way of reconnection. We have to assume the spatial and temporal dependence of the heating. But we do that, then the models give us the predicted emission pattern. We compare that with observations and see, well, is there a good agreement or not? If not, we change our assumptions about the heating, do it again, And hopefully, through that process, we can ultimately pin down the properties of the nanoflares that are heating the plasma. So let's look at a couple examples of this. These are two field-aligned hydro models. Typically these are called loop models, but really they refer to the individual strands. A loop, as I've argued a little while ago, is a multi-stranded structure. Okay, so this is the evolution of the plasma within a single strand. On the left, I show a case where there is nanoflare heating of low frequency. So there's a long delay between successive nanoflares. The delay is longer than the cooling time. So in fact, there's a delay of 3,000 seconds before the next nanoflare goes off. So this shows in solid here, this is the temperature averaged along the strand as a function of time, and the dash is the density as a function of time. The behavior is very well known. The nanoflare goes off, we have an abrupt increase in temperature, then we have cooling, dominated initially by thermal conduction, that are giving way to radiation cooling. But this thermal conduction energy, then, this is dumped into the chromosphere. It heats the chromospheric plasma, raises its pressure, and the plasma expands into the loop, and that is the evaporation. So the density in the loop rises from evaporation. Eventually, as cooling continues, the thermal support declines, and there's a slow draining of the plasma. But a key point is that the vast majority of this plasma is evaporated plasma. The original density was way down here. So this is the density of the directly heated plasma. It's not very large. So most of what we see in this simulation is evaporated plasma. Now on the right, let's look at a different case. In this case, we have what we call high frequency heating. The interval between successive heating events, successive nanoflares, is very short compared to a cooling time. Well, now, quite obviously, there's only a little cooling before the next event goes off, so the temperature fluctuates about a mean value, likewise for the density. Now, in this case, most of the plasma is directly heated plasma, not evaporated plasma. So it's really a very important difference here. I should say that in these two cases, the time average heating is the same. The nanoflares are 10 times stronger on the left, but 10 times less frequent. All right. Now, if we were able to observe, to spatially resolve individual strands, we could easily distinguish between these two possibilities. But in fact, that's not possible. The strands are much too small, and we're always looking at many, many overlapping strands. And so we're forced to infer the properties of the heating based on the collective emission from these many overlapping strands. And we can actually do fairly well. It's kind of surprising, really, but we have some techniques for really getting a handle on the heating. First of all, we can look at the slope of the differential emission measure distribution. I show on the bottom the time integrated differential emission measure for the simulation above. So differential emission measure, this is essentially plasma as a function of temperature. So in the low frequency case, we have a wide range of temperatures present. We have a broad DEM. In the high frequency heating case, there's only a narrow range of temperatures, so the DEM is very narrow. And the slopes of these distributions are very different, shallow slope versus steep slope. We can and have looked for that in the data, and we can make different inferences from it. Something else we can do is look for the presence or not of very hot plasma, because only low frequency heating can produce this very hot plasma, plasma with temperatures approaching and perhaps exceeding 10 million degrees. We don't see it over here with high frequency heating. So for that reason, we sometimes call the presence of hot plasma, very hot plasma, the smoking gun of nanoflares. We can also look for evidence of cooling. Now, you might think that that's impossible to find because we have all these overlapping strands. How in the world are you going to tell if something is cooling? Well, in fact, Nikki Val and I have developed a time lag technique that looks at correlations among observing channels that are sensitive to different temperatures. And this technique is able to pick out signatures, very clear signatures of cooling, even when there are literally thousands of overlapping strands that are heated randomly. They're out of phase from each other. Lastly, we can look for subtle fluctuations in intensity or subtle deviations from symmetry in distributions of intensity. And these have implications. So all of these various techniques are pointing to the same picture. And that is one in which within active regions, there is a whole distribution of nanoflare frequencies. We have low frequency nanoflares, high frequency nanoflares, everything in between. And the characteristic frequency, or the median frequency, if you will, is comparable to a cooling time. But there's a whole range of frequencies that are present. Okay, on the bottom here, I list some upcoming missions that are going to provide us with even better data for better constraining the nanoflares. And I would point out in particular, EUVST, this is basically Solar C. And this was recently selected. It was announced 2 weeks ago or so. This is very exciting. This mission is going to provide lots of great data for understanding not only nanoflares, but also full-blown flares. Okay, well, one of the holy grails of coronal physics is to spatially resolve individual strands. And it's not possible with traditional optics. You know, diffraction limits on the optics prevent us from getting down to the resolutions we need. You know, we believe that these strands have a diameter of order 100 kilometers, and traditional optics just can't get down there. However, there are ideas to use photon sieves, which are essentially fancy Fresnel lenses. And these are able to get down to these resolutions of less than 1/10 of an arc second. So there are two concepts that are being developed. One is called visors. This, in fact, it has been funded and is literally being developed. I mean, they're cutting hardware. This is an NSF CubeSat. There's another concept for a more ambitious mission called Sharpie, but that hasn't been funded yet. Okay, so there was some optimism that we can actually see these individual strands, but I myself was a bit pessimistic because I figured even with this really great spatial resolution, you still have the problem with the line of sight overlap. You know, we're integrating through this long path length. We have many, many strands. You know, are we really going to be able to pick out individual strands? So I figured I would look into that more seriously, more quantitatively. So I constructed a model, and that's shown here. This is really quite a realistic model of nanoflares in an active region. The field of view here is only 1,000 kilometers. So this whole thing here would correspond to one typical pixel in today's observations. Okay, but with the resolution of these photon sieves, we can see much smaller scales. So within this field of view, I have 1,250 strands with a diameter of 200 kilometers. And these are heated by nanoflares in what I would argue is quite a realistic way. I mean, the nanoflares are selected randomly from a power law distribution of nanoflares. And that slope of that power law has a value similar to what we infer from various observations. What else? The total energy going into the system is similar to what we need for active regions. You know, the flux, the Poynting flux of energy is the well-known 10 to the 7 ergs per square centimeter per second that people like to talk about. The depth of this thing is realistic. It's 50,000 kilometers in depth. That's a typical depth of an active region. And so I've got this simulation here, and I've simulated observations on the left here in the iron 16 line at 335 angstroms. This emission is formed at about 3 million degrees. And on the right, simulated emission in the iron 18 line at 94 angstroms. That's formed at quite a bit higher temperatures, more like 8 million degrees. So let me run this movie. There we go. And in fact, you know, which was not my intuition, we really can find clear, direct evidence of these strands. We really can resolve them and see them as individual structures. So this is very encouraging. I think the future holds some exciting promise. And I would point out that the structures are more visible on the right in the hot line, which is no surprise because the hot plasma is very short-lived. Recall on that plot of temperature versus time that there was very strong cooling right after the nanoflare. And so these really, really hot strands are relatively rare, and so there's less of an overlap issue. All right, now what? Yikes, no. Am I still with you guys?
Yeah, Jim, but
Everything.
somehow you close the presentation.
I know, I see that. So let me try it again here. All right. There, are we back?
Yeah.
Okay, so let me go down to where I was. We were here. I'm going to pass that now to go to this one. All right. So let's see. How are we looking for time? Okay. I see. All right. Oh, no, sorry. We've already seen that one. And this, okay, now here, all right. So now I've talked about the temporal dependence of the nanoflares and how important it is, low frequency versus high frequency. It turns out the spatial dependence, where along the strand the nanoflare occurs, in general is not very important. That's because thermal conduction is so efficient at distributing the energy along the field. However, there's one very, very important exception, and that gives rise to a phenomenon, really fascinating phenomenon, that's called thermal non-equilibrium, or TNE for short. Turns out that if you have steady heating or very high frequency heating, which is effectively the same thing, and that heating is concentrated at low altitudes in the corona, down low in the loop legs, then there is no valid equilibrium. Even with truly steady heating, there's no equilibrium available to the system, so it's always evolving, endlessly evolving, goes through various convulsions and produces these condensations, which you'll see right here. So this is going to be a movie showing temperature as a function of position along a strand. So here, chromosphere on one side, chromosphere on the other side, the two transition regions, and the coronal section in between. All right. Now, the heating in this simulation is absolutely steady, never changes, but its magnitude decreases exponentially with distance moving up from the foot points. It's the same on both sides. This is a symmetric loop. So let's see what happens. Again, perfectly steady heating, yet there is constant evolution. And you see in particular this thing happening here. This is up at the apex of the loop. There is a catastrophic cooling, and we form a very cold, chromospheric temperatures and dense condensation, which then slides down the loop leg and things repeat. Okay, well, what's going on here? Well, basically, the lower legs of the loop, which have very strong heating, they're trying to establish an equilibrium. And they need to do that by increasing the density. So evaporation occurs. But that evaporated plasma, of course, doesn't stay in the lower legs. It fills the entire loop because the gravitational scale height is very large. So up at the top, where the heating is minimal, we have too much density. And so that high dense plasma, it radiates strongly, and then it gives rise to this cooling, this catastrophic runaway cooling. Okay, so this phenomenon of thermal non-equilibrium is widely agreed.
Jim,
Yeah.
while you are here, you told that everything is symmetric. Could you comment why some frames are not symmetric?
Yeah, why does this thing not sit at the top? That's due to either just small noise in the system, maybe created by numerical round-off errors. In principle, this thing should stay right dead smack at the center here, but these little effects cause it to slowly shift to one side. Then once it starts to, then it runs away. But yeah, in principle, it's symmetric. Okay, and we've looked at cases of asymmetric heating, and they have very important consequences, and I'll get to that in a second. But first, I just wanted to point out that this basic process here is widely agreed to be the explanation of coronal rain, phenomenon that's well observed. It's believed to explain the formation of solar prominences. We have this cold plasma high up in the corona. That plasma gets there by thermal non-equilibrium. And, Judy Carpin and Spiro and others, myself as well, have worked on that. There's a newly discovered phenomenon called long period loop pulsations, which is probably due to this TNE. And some people have suggested that, in fact, it may be very widespread. So we need to investigate that. But this gets to your question a little bit, Gregory. By making some simple assumptions, it's possible to derive these expressions that give the conditions that must be satisfied to get thermal non-equilibrium. Now, I don't expect you to understand this, but I just want to make the point that the top condition here, this basically says that the heating has to be sufficiently highly concentrated in the low corona. Then this second expression here, this has to do with asymmetries. This says that if the asymmetries are too great, you don't get TNE. Instead, the loop settles into a nice equilibrium. It's not a static equilibrium, but it's a steady flow equilibrium with flow going from one end of the loop to the other. So both of these indicate that the spatial dependence of the nanoflares is important, how high it is in the corona and whether or not it's symmetric. All right, so I've talked about very small scales, the current sheets that reconnect. I've talked about intermediate scales, such as the coronal loops, the multi-stranded coronal loops. We find that heating is also varies on very large scales, scales of an active region, and that's demonstrated here. This is from a paper by Harry Warren. Here are 5 active regions, magnetograms are on the left. Then we show the active regions as seen by AIA in 4 of its channels. There's the 171 channel here, 335 channel, 94 channel, and finally here, this really isn't a channel. This comes from combining channels, and it's an attempt to isolate the very, very hot emission. So for the most part, temperature is increasing from left to right here. Okay, and you see quite clearly that there are systematic variations across these active regions. And we find that the plasma is hotter, and therefore the heating is stronger in the cores of the active regions. We find that these distinctive loops are more prevalent out in the outer parts. So this is something we have to understand as well, if we really want to say that we understand coronal heating. And this is in fact providing us with useful clues about the heating, ways that we can strain the heating. So how do we do that? Well, we do that by building models of active regions, generating synthetic images, and comparing them with actual ones. So one type of model is an MHD model. People like to call these first principles models because the heating comes out of the model. It's not specified somehow. So in these models, there's some kind of driving imposed in the photosphere. However, the driving does not have anywhere near the complexity of real convection. And furthermore, the distribution of flux in the photosphere is not nearly as clumpy as it is in the real photosphere. And as a consequence, these so-called first principles models do not have these thousands or even hundreds of thousands of current sheets that we know exist in real active regions. And so the heating in those models is primarily from ohmic dissipation of large-scale currents. It's not from reconnection of many, many small current sheets. So we don't know if the heating really represents the corona well or not. It may be that this heating is a good proxy of the real heating mechanism, but maybe not. Yeah.
5 minutes.
5 minutes. Okay, thank you, Barry. All right. So another approach is to take the approach of the GX simulator tool. This is something that Gregory has developed together with Jay Lunita. Del Gary has been involved. I've been involved a little bit as well. And the idea here is to take a magnetogram, construct an extrapolated field, a force-free field, for example, then populate the field lines with plasma using the output from field-aligned hydro simulations. So again, in those simulations, we have to specify the heating, and we can specify a parameterization if we want. For example, the heating rate, the volumetric heating rate, may vary as the square of the field strength. Makes sense because it's magnetic energy. And perhaps inversely, it varies inversely with the loop length. Well, why this? Well, it turns out that this is what you expect if the heating comes from the field being stressed and reaching a critical shear angle. So you can assume some kind of parameterization like this. Then you can take this heating and you can put it into the corona either with low frequency nanoflares or high frequency nanoflares. You build a model of the corona, you generate synthetic images, and you compare with observations. So that's what's been done here. On the left are the actual AIA observations of this active region in the different channels. In the middle here are the synthetic images created with GX Simulator, assuming this form of heating and also low frequency heating. And then finally on the right is again the GX Simulator simulated emission, but now assuming steady heating. And there are differences. We can compare with the observations, we can adjust our assumptions, and hopefully eventually find a good fit. And that then will tell us what the properties of the heating are. Now, I would point out that there are significant differences between the impulsive heating and the steady heating in these models. It might not be so obvious, but that's partly because the bright stuff here, this is all transition region emission. In these AIA channels, even in the channels that are called coronal channels, much of the emission is from the transition region, not the corona. And if we compare the coronal emission in the impulsive versus steady cases, there are significant differences which provide us with a real handle on what is going on with the heating. All right, time is running out. I've given you kind of a whirlwind tour of coronal heating. I've shown examples from work that I've been involved with. That's just for convenience. In fact, many people are working on these problems and doing great things. Here's a quick summary. Understanding coronal heating requires multiple approaches, all of which must come together in a comprehensive, unified, self-consistent picture. Okay, the reconnection onset conditions, they control the energies and frequencies of the nanoflares. The radiation spectrum in turn depends strongly on these energies and frequencies. Coronal loops are produced by storms of nanoflares. There's some sort of collective behavior that we still need to understand, maybe an avalanche type process. Thermal non-equilibrium occurs when there is low altitude, high frequency heating. And finally, the properties of nanoflares vary systematically across active regions. Now, if I do have a minute or two, you decide, Gregory. I was hoping to spend
Yeah, you have, of course. Yeah, go ahead.
It's okay. All right, thanks. So the sulfur team deals primarily with flares and eruptive flares in particular. You know, I kind of wish we would also consider non-eruptive flares because I think the differences can be very instructive. But we're talking mostly about eruptive flares. So what are the differences between eruptive flares and nanoflares? Well, first of all, as I indicated when I was discussing reconnection onset, nanoflares are in the short current sheet regime. Eruptive flares are in the long current sheet regime. Nanoflares involve slow driving, and the photospheric motions are relatively slow. Whereas with eruptive flares, there's very, very strong driving of the current sheet. The CME is occurring, it's erupting quickly, it's stretching open the field, and the current sheet forming underneath is really being driven. So these could be important differences. Now, regarding the onset of reconnection, well, is it a natural sort of a tearing, like I've argued is the case for nanoflares? Or is it more of a strong localized forcing? You know, if we have these highly driven current sheets and eruptive flares, maybe there are places where the forcing is especially strong and it's really rapidly, you know, creating the start of reconnection at those locations. It's not so much a natural tearing. Now, what about the nature of the current sheets? You know, current sheets can form in a couple of ways. They can form at separatrix surfaces. Any kind of photospheric motions will turn separatrix surfaces into current sheets. That's the situation for nanoflares. But current sheets can also form from collapsing X points. And certainly the breakout reconnection that initiates the CME that ultimately produces the eruptive flare, that current sheet forms from a collapsing X point. But what about in the eruptive flare itself, that current sheet? Well, the initial reconnection, I would argue, happens at a separatrix surface. But if the subsequent evolution involves a succession of what I might call macroscopic islands or plasmoids, then those islands are forming in current sheets that are resulting from the collapse of X points from the previous islands. You know, are there differences in the behavior in these two types of current sheets? You know, separatrix current sheets could be quite uniform. Clearly, current sheets formed by collapsing X points are not uniform. Then I would ask, what do we mean exactly by turbulent reconnection? I think it means different things to different people on the sulfur team. We had a brief discussion of this during the CLC meeting earlier this week. You know, if the reconnection involves the formation of islands, but a limited number of islands, is that turbulence? Or to call it turbulence, does it have to be a very complex multi-scale mess? I think we need to come up with a uniform definition, a definition that we all agree to. And then for these two situations, are there different reconnection rates? Is the particle acceleration different? Now, as we have discussed before, there is oftentimes a transition from fast reconnection, where the reconnection rate is 0.01, to very fast reconnection, where it's 0.1. And this seems to happen when the kinetic scales are reached. Is this a universal thing? Does this happen in all cases? Then I would ask how important it is to resolve the current sheet in eruptive flare simulations. Maybe it's important, maybe it's not, maybe it depends on what you're trying to look at. But I think this is something we really need to address very carefully. So there's, in fact, a lot to address, and hopefully we can do that in phase 2 of sulfur. So thanks a lot for your attention, and I welcome any comments you have or criticisms or questions.
Yes, thanks, Jim. I enjoyed your talk very much, and we are almost open to questions. Just minor correction. When you refer to JAX simulators, and first credit has to go to Jello, not to me.
Yeah.
So,
Yeah.
so please, questions to Jim. Yeah, go ahead, Leon. Yeah.
Yes, very nice talk, Jim. I have a question regarding the MHD part, the initial part of your talk, where you mentioned that you basically model a tearing mode. And in those cases, indeed, there are two different cases, the long wavelength limit
Yeah, okay. Now, I only caught part of that because you were breaking up, but you pointed out that the different modes grow at different rates, but you said that the rate of all the modes, even the fastest modes, is very, very slow, too slow to explain the reconnection rates that we observe.
Right.
I absolutely agree with that. Oh, sorry? Yeah.
Right. In particular, if you take a realistic Reynolds number in the solar corona, they become too slow. Maybe you can address that.
Yeah.
That's all.
So yeah, we have thought about that very, very carefully. And my response is this. The growth rates are slow, but they are not incredibly slow. So as the current sheet is thinning, the growth rate is getting faster and faster and faster. And you eventually get down to a current sheet width, which is not that narrow. I mean, it's much fatter than the Sweet-Parker width. It's way bigger than kinetic scales. But even at that size, which I think is like 100 meters or so, the growth rates are fast. The growth times are, of order a second or a few seconds. So the Turing mode is important for getting things going. Eventually, it has to transition to something faster. And so that's where you have this, when the Turing modes become nonlinear, they start to interact, and that causes other things to happen, and then things end up becoming very, very fast at that point. But the Turing modes are certainly fast enough to explain the initiation. We have looked at that very carefully, taking realistic Reynolds numbers and all that.
Okay, we have to move on. Martin, please go ahead.
Yeah, Jim, so nice talk. You started off by talking about the difference between reconnection heating and wave-driven heating. My question is, surely an important output from reconnection will be waves, especially the guide field reconnection you're talking about for nanoflares. Can you say anything about how much energy comes out in waves, what the spectrum might be, what the frequencies, things like this?
Yeah, no, I can't. And I have asked that question myself. Surely you're right. Unquestionably, there are waves being generated, and those waves will dissipate, remote to the region.
Non-locally, yes.
Yeah. Now, it's a difficult thing to work out from the simulations. I asked that question just the other day, and Cindy Cattell sent me a paper. I haven't looked at it yet, but from what I can tell, the feeling is that the energy going into waves, and I mean real waves, real oscillations, not kinks that propagate outward, but real oscillating waves, that energy seems to be small compared to the energy going into the flows, which gets thermalized. But I think that's a question that we need to answer more quantitatively.
Yeah, I mean, I'm thinking that comparable amount of energy goes into waves, and if the waves get to the chromosphere before the thermal conduction front, you get FIT fractionation.
Right.
The waves don't get there before the thermal conduction front, you don't.
Mm-hmm.
And this might be an important...
Right, that's one of the important things that we should address in sulfur phase 2. I agree with you.
Yep, okay.
Okay, next question. Amir, you raise your hand.
Great talk, Jim.
Thanks.
So you talked about how low frequency versus high frequency, the origin of the plasma appears to be different, chromospheric versus directly heated. Does that have implications for abundances in addition to the DEM, and what observational signatures might help differentiate that?
Well, what a surprising question from you, Amir.
I know.
One of the upcoming missions that I listed,
asking because I actually don't know what the implications of the abundances are, and I'm wondering what to look for.
Well, I listed some missions at the bottom of one slide, upcoming missions. One of them is CubeX. It's a NASA CubeSat that Amir is leading. And so one of the goals is to understand the distribution of plasma as a function of temperature and to look for FIP issues. So, Martin would be the person to answer that question. right? So the traditional view was that if you can evaporate plasma from the chromosphere, it has photospheric abundances. Otherwise, it might not. Go ahead, Martin.
Yeah, I was going to say that if the waves from reconnection can get down to the chromosphere before the conduction front, the fractionation process is actually quite fast because you're only moving ions over elements over a small region, but for that a magnetic field of I don't know, a few tens of Gauss in the corona, so active region rather than quite some. So yeah, I think that's where the fraction of the fit would come from.
But the question is the question is what kind of abundance signatures would you look for to try to distinguish between high frequency versus low frequency heating, or is it not possible because of all of the superimposed?
My suspicion is that if you consider a single field line, you need to have probably low frequency heating to get significant fractionation. If you've got a continuous stream of stuff moving, it won't fractionate.
So you're saying high frequency would look more photospheric?
Probably, yeah. That would be my guess. Because upflow velocities quench the fractionation.
Okay.
Well, on the other hand, high frequency means that you're not getting that much evaporation. Most of the plasma you're seeing is the plasma that was already up there.
Right.
In other words, you're saying there you have two competing effects that are going in exactly the opposite direction.
Yes.
I wonder, are there other questions? So I don't see any raised
I have a
hands.
question. Gregor, this is Spiro.
Okay, go ahead, please. Yeah.
I have a comment anyways. So Jim, on this issue about the nanoflare versus eruptive flares and this question about the current sheet, you raised the important point that the formation process is critical to understand the phenomena. Now, my formation process for both nanoflares and for large flares is basically the same in the sense it's due to the slow driving from the photospheric motion, which puts stress in the coronal field. The key question is what happens next. So in other words, that the reconnection begins, but then what happens? Is it that the system kind of erupts upward, and because of this eruption can can keep driving the current sheet even faster, even stronger, and lead to more and more reconnection, even faster reconnection? Or is it the case that the reconnection that results from the current sheet, starting to disrupt, just fizzles out the current sheet? So in a sense, the way I would phrase it is that in the nanoflare case, current sheets form all over the place, and then there's a localized reconnection that takes away the energy out of that current sheet. Whereas in the flare, what happens is that the coherent motion, kind of like a resistive instability, that lets the system take out the energy by reconnection at a single current sheet that keeps reforming as a result of the mass motion or as a result of, the dynamics. See what I'm getting at here?
Yeah, absolutely. I agree completely. That is kind of related to this point I made about the coupling of the reconnection with the surrounding larger scale field. That can be critical. I agree completely.
That's exactly right. That's really, in a sense, I would argue, more important than the onset, because that tells you how much energy you're going to get out. Right.
Well, okay. I'm not sure I'd fully agree on that. I mean, as I tried to stress at the beginning, the onset tells you how much energy you can build up, which is available to be released. Then, as you say, the question is, once you start to release it, how much of it can you release? Does it fizzle out? Does it keep going? But in the case of nanoflares, if they happen too easily, you don't get much stress in the field. So the nanoflares are going to be weak. And not just the individual nanoflares, but the total heating of the corona will be weak. It's not simply a question of, do you have large nanoflares occurring infrequently or small nanoflares occurring frequently, but the total energy release is the same, that energy release being determined by the driving at the photosphere. It's more than that, because the Poynting flux injected into the corona by a given driver flow will depend upon the amount of stress that's in the field. So not only the frequency of nanoflares, but the total energy heating the corona depends upon the onset conditions. So
Sure.
that's nanoflares. But certainly you're right for flares. You know, and the onset's not so critical for flares. I mean, the onset of the breakout reconnection is critical because that tells you, you know, how energetic the CME can be, which, you know, limits how energetic the flare can be. But the flare reconnection itself, once the CME gets going, its onset is not really a big issue. But a really big issue is how long can you sustain that reconnection, like you described?
I believe the speaker has to join next meeting right now. So unfortunately, I have to close the discussion, even though it's very, very interesting and instructive. So thank you very much, Jim, and thank you all participants for joining.
Yeah, thanks for your comments. Really good comments.